Hey, hello there. So, gonna talk about today's Leetcoding challenge question. It's called majority element. So we have an array of size n, and we want to find the majority element, which is the element that appears more than half of the time. So if we have an array of size 3, the threshold here is 3 divided by 2, that's 1/2. We take the floor, that's 1. We have to be strictly more than that, so the element needs to be appear at least twice. So for the first example, we have 3, 2, 3. The element 3 appear twice. That satisfies the threshold condition here, so it's the majority element. The second example, we have 2, 2, 1, 1, 1, 2, 2, 7 elements. So if we work out the number threshold, it's 3/2 floor 3 plus 1 4. So we need to find an element that appears at least 4 times, which in this case is the number 2 here. So it's a pretty straightforward question. If we go to the count the number of times every element appears in the array and compare that with the threshold, it will be a linear time algorithm with potentially linear space requirements. The space is going to be half of the array size, because if in the worst case there is this one majority element that appears half of the time, a little bit more than half of the time, and all the other elements are distinct, the total number of unique elements is still going to be bounded by n divided by 2. So that's but we drop the constant, so it's still linear in both time and space. So the code is pretty simple. We're going to have a hash map to store the number of times each element appears. For each number in this array, we're just going to increment that count. And we check if the frequency count is greater than the threshold, then we can just return the number. So since this question is guaranteed that there would be a majority element, so it's always there, so we can be sure that the function will always return some number based on this question. So that's pretty much the solution if we use hash map, and it's a linear time, linear space. The problem is that it's basically treating this problem very literally. It's using the definition to solve this problem. It's not utilizing the property that this definition brings to this question. So but before I go to that route, a much better solution is that to mention that since that the element here are integers, we can also do bit counting. So the argument for that, let me quickly spend like 2 minutes talk about that. So let's say we have we're working on the example 3, 2, 3. So the binary representation is 1, 1, 1, 0, and 1, 1. So if we just instead of counting the integer number, we count the bits. It will be 3, 3, and 2. So the final number has to have a 1 bit in the 2's location, and has to have a 1 bit in the 1's location, because the counter argument, the proof by contradiction is that if the majority number has a 1 bit in one of the location, don't have a 1 bit in one of the bit location, then there is no way when we do this counting, that location will be greater than the threshold. That count for that location would be, the count of the 1 bit in that location will be greater than the threshold. There's no way that's the case, because you only got majority element minus 1 in number of times of other elements. Even all of those other elements have a 1 bit in that location, is still one shot to be passing the threshold. So we can just prove that instead of counting the number, we can count the bits for each location. And in the end, we just for every location that has the 1 bit count greater than the threshold, we just flip that bit, we just turn on that bit for the integer number, and return that whole number as the majority element. It has to be that majority element in there. The benefit of doing this bit manipulation kind of solution is that you save the space. If you're working with 32-bit integer, the memory size is going to be 32, so it's effectively constant compared to the hash map, which can grow to linearly with the input size. So that's the benefit. But doing this shifting bits, counting and stuff, it takes a little bit longer time, even though it's still linear in time, but can actually run slower than the hash map. Yeah, but the benefit is it saves a little bit of space. So but the bit counting is also just using the problem's definition. A little bit about the property it brings, but not as good as the better solution. So the better solution is try to reduce the problem into the same problem, essentially the same problem, but of a smaller size. So instead of finding the number based on frequency count, we can actually try to divide the array into two sections. So let's say that we have an array, and we find the section that's from the beginning towards the ith location, and the stuff that's afterwards. So let's say that the majority element is the number n here, and if we find an array such that the number of times the majority array appeared in this first part is equal to I divided by 2, so the length of the first half divided by 2. Which means that the actual majority element in the first half that we find is just a one shot to become the majority in that chunk. So if we find such a division of the input array, we can be sure that in the second chunk there has to be greater than the length of the second chunk divided by 2. Because the element n is the majority element. In the first half, it's not. It's almost there. And it's exactly taking half of the number of elements in there. So for this number to be the majority element for the full array, in the second chunk, it has to be the majority element. So whenever we find an array with some elements that appears half of the time, we can pretty much just safely disregard that chunk of the array and run the algorithm on the second chunk, because essentially the second chunk is the same problem but with a smaller size. So we want to do this. So how do we know that when we but this is based on that we know the element is n. We kind of counting, does it just so happen to be one half of the time? But it turns out when we try to find the first half, it doesn't matter which element we treat as the candidate. Once this element only appears half of the time, the true majority element in that chunk is also gonna happen appears less than that amount. So if we safely if we disregard that first half, it's always guaranteed that the true majority element in the second half there is gonna be the majority element. So we still have this property. So we just basically have a candidate element that we randomly grab, maybe the first element in the first chunk, in the part that we were working on. And once we find a chunk, find the termination location I, where the most frequent element in there occupies half of the time, half of the slots in that chunk, we can just disregard that part and looking into the latter part, the same problem of a smaller size. And the base case is we have so in the end, if we have ARR I plus I and on to be of size 3 maybe, so it will be a few cases like ABA, AAB, BAA. So it will actually bring to be reduced even further. So if we see AB, so that's the ARR towards I kind of case. We have a size 2 array. Each element appears exactly once, so we can actually disregard that, and we find one last array there that contains only one element, which just so happen 1 is greater than 1 divided by 2 floor. 1 is actually greater than that number. That threshold for an array of size 1 is 0. So the A has to be the majority array, a majority element in the full array there. If we, in the case of AAB, then we will never find an I in that case, and so in the end we just return A as the majority element. If we are in the BAA case, we will terminate and disregard the BA part, and that left us with the majority element to be A. So this is the base case, and it's got I'm not doing formal proof here, but by doing this, picking the first element to be the candidate, once we find the reach the condition that this candidate only appears exactly half of the time in the continuous chunk until i's location, we can disregard the first I element altogether and only focusing on the and call the function again on the second half there. Whenever we reach the base case here, we can pretty much pin down exactly to where this majority element really is. So that's sort of I think it's it should be qualified as a divide-conquer algorithm. So yeah, just gonna code this up very quickly. So the benefits about this solution, it's a linear time and a constant space. All you store there is the count for the candidate and the candidate value as well. So only 2 variables. My camera is blocking me. So if the count is equal to 0, that means so when we try to find this array until the I, where the count of the element that we pick is exactly half of the time, is just by counting the number of times it appears. So whenever the candidate, the n appears, we increment that count. Otherwise, we decrement. Once the count reaches 0, that means we reached the location, the position I, where this condition satisfies. So that's just using one variable to keep track of that. And that's the case when we can disregard the first and reset the candidate and focusing on the second half of the problem effectively. But I'm not coding the recursive solution, because recursive, I think you could code it recursively as well, I think. So if the count is 0, we update the candidate to be the this number, which will be the first number in the second half, in ARR I and on. So that's the number we are looking at. And we gonna increment the count. So in the end, we just return this candidate. So yeah, so this is pretty much the code. Yeah, it's a linear time and a constant space, and it requires you to analyze the property of the arrays based on this definition. While the hash map solution only requires you to use the definition as it is. It's not deriving any kind of property of the array from that definition. So I think the second one is it's pretty cool. So yeah, that's the question.